Good morning, madam. Dr. Disi and Dr. McRae, madam, good morning. For you, good evening. Share screening within 1 minute we will give, madam. You can share your screen.
Hereafter.
Hello. So you're just checking mine?
Yes, madam. Yes, madam. You are audible.
Okay. Now let me see if you can see my share screen. Can I just check my share screening once?
Yes, madam. Yes, madam. Good morning, all of you. Good morning, Professor Ken Murthy garu. Good morning, Dr. Mekre madam, and good morning, Disi madam. One more Vasundhara and Dr. Vasundhara madam have to come. Some problem is there in login. Within 1 minute, she will join, madam. Then we will start the program. Thank you, madam.
Good morning, everybody. Namaste, Masharu.
Madam. Madam, are you ready, madam? Vasundhara madam, good morning, madam.
Yeah.
Good morning.
Good morning. Good morning to everybody. Namaste, Masharu.
Can I start, madam?
Okay. I'll check later, maybe. Yeah, you can start. Maybe at my time, I'll check the share screen.
Yes. Okay, madam. Then I'll start.
Yeah.
Good morning to all of you. Today, on behalf of St. Joseph's College for Women, Autonomous Visakhapatnam, and Uttarandhra Society for Mathematical Sciences, that is UASMS, and Professor S. Meenakshi Sundaram Memorial Society, SMSMS, I welcome to the second day webinar session, that is 2-day international webinar on recent advances in mathematics and COVID-19. Let us start with the college prayer song.
Lord, make us instruments of your peace. Where there is hatred, let your love increase. Lord, make us instruments of your peace. Walls of pride and prejudice shall cease when we are your instruments of peace.
This is our college prayer song sung by SJC Coil. I might likewise want to offer my special thanks to our resource persons for the day. Professor J. Vasundhara Devi, Department of Mathematics, and Gayatri Vidya Parishad, Professor V. Lakshmi Kantam Institute for Advanced Studies, Gayatri Vidya Parishad, College of Engineering, Autonomous, Visakhapatnam. Dr. Jahia Trisi, Professor and Chair, Department of Mathematics, Illinois Wesleyan University, Bloomington, Illinois. And another resource person of today's, Dr. Farzana A. McCrae, Department of Mathematics, Catholic University of America, Washington, D.C. And last but not the least resource person, Dr. KNV Varaprasad, Associate Professor, Department of Pure and Applied Mathematics, Guru Gausisas Das Viswavidyalaya, a Central University, Bilaspur. On behalf of St. Joseph's College for Women, Autonomous, Visakhapatnam, we welcome to all and our special thanks to our today's resource persons from the USA, Dr. Drisi and Dr. Farzana A. McCrae, who actually accepted our invitation, and we are overwhelmed to have them on board for the resource talk. Now I invite Mrs. A. Parvati, Assistant Professor, Department of Mathematics, to introduce today's first resource person, Dr. Jahia Drisi. Over to Mrs. T. Parvati.
Thank you, ma'am. Good morning, ma'am. Good morning to one and all. This is Parvati, Assistant Professor, Department of Mathematics. I am so excited to be here today and to have the opportunity to introduce our guest speaker, Dr. Jahia Drisi. Dr. Jahia Drisi, Professor and Chair, Department of Mathematics, Illinois Wesleyan University, Bloomington, Illinois. Dr. Drisi's research interests include various areas in ordinary differential equations, focusing more recently on fractional differential equations. As part of her research, she co-authored with Dr. McCrae and Dr. Professor Vasundhara Devi a number of papers, 2 book chapters on the qualitative theory of various types of differential equations. She co-authored a research monograph with the illustrious Professor V. Lakshmi Kantam. Today, in this session, she will present a general introduction to fractional derivatives and fractional differential equations. I am very thankful to our Sujata ma'am for giving me this wonderful opportunity. Thank you, ma'am. Thank you.
Thank you, Parvati. Now I invite Mrs. D. Rajani, Assistant Professor, Department of Statistics, to introduce today's second resource person, Dr. Farzana A. McCrae. Over to Rajani.
Thank you, ma'am. Good morning to one and all. This is Rajani, Department of Statistics. It's my privilege to introduce the eminent speaker of the today's session, Dr. Farzana A. McCrae. Dr. Farzana A. McCrae, Associate Professor, Department of Mathematics, Catholic University of America, Washington, D.C. Dr. McCrae's research in the area of ordinary differential equations. Her most recent work has been focused on fractional differential equations, and she has, with Professor Vasundhara Devi and Dr. Drisi, co-authored a number of papers and 2 book chapters on the qualitative theory of various types of differential equations. She co-authored a research monograph with the eminent scholar Professor V. Lakshmi Kantam. Thank you.
Thank you, Rajani. Now I invite Mrs. K.K. Saujanya, Assistant Professor, Department of Mathematics, to introduce today's next resource person, Professor J. Vasundhara Devi. Over to Mrs. K.K. Saujanya.
Good morning, everyone. This is Saujanya, Assistant Professor, Department of Mathematics. It's my privilege to introduce the eminent speaker of today's session, Professor Vasundhara Devi. Professor Vasundhara Devi did her PhD with the eminent professor Dr. V. Lakshmi Kantam and co-authored a couple of research monographs with him. She had published more than 90 research papers in peer-reviewed journals and completed 3 research projects sanctioned by different agencies of Government of India. Fractional differential equations are one of her research area, and she collaborates extensively with Dr. Drisi and Dr. McRae. In this talk, she will present some of the recent developments in this area as the third speaker. Now, I request ma'am to take over the session. Thank you.
Thank you, Saujanya. Now over to Professor J. Vasundhara Devi Madam and her team, who will talk about developments in the theory of fractional differential equations. You can take charge.
Good morning, everybody. Among our speakers, Dr. DC will talk first. And Dr. DC could not be introduced properly, so I'd like to say a few words. Dr. DC is a professor in the Department of Mathematics and she's also chair of the department of Illinois Wesleyan University, Bloomington. And he co-authored a research monograph with Professor Lakshmi Kantam and has published extensively. We three, Dr. DC, Dr. McRae, and myself, we collaborate our research work. And she is very good in mathematical modeling. She's a very good researcher and a teacher also. Over to Dr. DC. Dr. DC, please take over.
Madam, you can take over the charge. You can proceed, Madam. Proceed, Madam. You are
Yes.
here. Yes. Okay.
Okay.
Okay,
Good
madam.
morning, everyone. First,
Good morning.
on behalf of my co-presenters and myself, I would like to thank the organizers of this webinar, mainly Dr. Captain Sujata, St. Joseph College for Women, and the Uttara Andhra Society for Mathematical Sciences. So thank you for inviting us. We're honored with this invitation, and we're very happy to participate. So I'll go very briefly over introduction. I'm Zahia Drisi from Illinois Wesleyan University, and Dr. McRae is from the Catholic University of America in Washington, DC, and Dr. Vasundhara Devi from the Gayatri Vidya Parishad College of Engineering in Vishakhapatnam. I was going to tell you what brought the three of us together, but I guess from the introductions that you've heard about us, you know that we have had a long-standing research collaboration. But I can also add that the three of us share also the fact that we are all, or we're all, the Professor Lakshmi Kantam students. The presentation that we prepared for you today is, let me go to my next slide. The title was given to you earlier. It's Development in Fractional Differential Equations. And we've divided the talk into 3 parts.
Dressing, ma'am.
Yes. Yeah.
So there is your screen is not shared, ma'am.
I'm sorry?
Please click on screen share, ma'am.
Oh, okay. I shared it earlier.
Yes, ma'am.
Okay.
Your presentation is not visible, ma'am.
Okay, so let me, how do I get back to that? I don't have, okay, let me.
Just click share
Sorry
screen.
about
ma'am.
that. Yeah, I'm going to share it now. Tell me if,
Yes, ma'am.
can you see it?
Now it is okay, ma'am.
Okay, it's
Full
okay.
screen. Full
Yes,
screen.
madam.
Okay.
Just click on view. Play to start. Okay, ma'am.
Okay, right. So I'm going to, okay. Can you see it now?
Yes, ma'am. Thank you.
Okay, good. So I was saying that the presentation today, let me get to that slide again. The presentation today is divided into 3 parts, and we each are going to cover 1 part. So I'll begin with the introduction, And we were told that the audience today is a general audience. So we thought it would be appropriate to begin with some, the general survey of the development of fractional calculus, and also to give you some definitions of, or the idea how some of the fractional derivatives and integrals were developed. So I'll do that, and then I'll pass the baton to Dr. McRae, who is going to tell you about the existence, the results of initial value problem for a fractional differential equation. And the third part is going to be covered by Dr. Devi, who is going to tell us about recent development. One thing I want to mention at this point is that there is no general framework for fractional calculus. There are many different definitions of integral and fractional derivatives. And for that reason, the field is still evolving, and there are still new definitions that are proposed. And that's what Dr. Devi is going to talk in part. She's going to mention that. All right, so about what I'm going to tell you, so general introduction. In fact, the fractional calculus is not a new branch of mathematics. It is as old as the classical calculus. That means it dates back to the end of the 17th century when Leibniz and Newton were working on the foundation of the classical calculus. And the word, the name fractional, as the story goes, is originate with Leibniz when he introduced his notation and showed it to the Marquis de l'Hôpital, who then asked him what would be the meaning of this nth order integer derivative if n were equal to 1/2, right? So n 1/2 is fraction, so fractional calculus, but in fact, fractional calculus deals with arbitrary order derivatives. So the order n could be a real number, a complex number, or it could assume a functional form, like you see here, right? So work on fractional calculus dates back to Leibniz and Newton's time. So I have listed here the names of famous mathematicians, and with the you see that it was an ongoing work, in attempting to come up with a definition of generalized integration and differentiation, in the sense of obtaining definition of derivatives and integrals for arbitrary order that would, in the special case of integer order, revert back to the classical definitions. And that is, in fact, still an open problems. Right? So there are several challenges, and I'm mentioning here a few. Dr. Devi later on is going to also address some other challenges, but the one I want to mention here have to do with the physical interpretation of these operators. So there is no acceptable geometric or physical interpretation of the fractional integrals and derivatives. By that, we mean we do not have the equivalent of what we have for ordinary derivatives, where we know what both the geometric interpretation and the physical interpretation of integer order, first derivative, second derivative, and so on. Nothing like that exists for fractional operators. This difficulty makes it more difficult the attempt at obtaining a definition of generalized derivatives and integrals, right? Because if the definition is to revert back to the classical case in special case of integer order, then there should be a clear link between the two types of derivatives, which does not exist. Another challenge is the fact that in initial value problems, where you need to specify initial values, if those initial values are expressed in terms of fractional derivatives, then there is no physical interpretation for those initial conditions. And the issue there is, if there's no physical interpretation, then one doesn't know how to measure, right? How to get those values. So that's another challenge. A third challenge I want to mention here is the fact that so this is challenged over time, since many definitions were introduced, and I should say that these definitions are oftentimes defined for specific applications. So you have definitions that are developed for a particular application, but these definitions are not interchangeable. They're not equivalent, they don't produce the same answers, don't have the same properties, etc. So that's another challenge if you're thinking in terms of coming up with this generalized definition. Throughout this talk, I mentioned in blue references. So for example, for the first two, for the physical interpretation, I mentioned the papers by Podlubny. Those are very good papers that have some number of references. Same thing, you have the classic text by Ross and Miller and Oldham and Spanier. In terms of applications, not surprisingly, because of the challenge I mentioned, it turns out that there were no applications worth mentioning until very late, right? So the first one is attributed to Abel in 1823 when he was working on the Totocron problem. Following that, another long gap in time for other application to surface. As you see, I give you an example here. Among the first applications in physics are the work that Mandelbrot did in 1982 when he was working in fractional geometry. Now, over the past several decades, the increased interest in fractional operators, derivatives and integrals, a lot of work has been done because it was recognized that these operators are non-local and therefore they turn out to be good tools for modeling memory-dependent phenomena. Okay, and I'm listing here a number of areas where a lot of work has been done using differential operators, integral and derivative operators. We've come across a number of papers on diffusion problems, mechanical properties of materials, and behavior of viscoelastic materials. So again, here are some references, the book by Diltham and the book by Ortiguera. Ortiguera gives some engineering applications, science application, etc. Diltham is a very comprehensive book that has a lot of applications, as well a number of definitions and their applications. The definitions that I'm going to talk about are the ones that are most relevant to differential equations and more specifically to the work that we have been doing. So there's Riemann-Liouville, fractional integral and derivative. This is a definition that has been used extensively in developing the theory. So useful in theory, but not so much in applications because of the issues I described, physical interpretation of the operators, as well as physical interpretation of the initial values. The other derivative is the Caputo fractional derivative. This is an adjustment that was made to the Liouville derivative. And the modification were made in an attempt to address the challenges that I mentioned above. So for example, the derivative of a constant, the Caputo derivative of a constant is equal to 0, which is not the case under Riemann-Liouville differentiation. There, the derivative of a constant is not 0. Another advantage of the Caputo fractional derivative is that the initial conditions can be expressed in terms of ordinary derivatives. And there are other advantages in terms of relationship between Caputo and Riemann-Liouville. As I told you, a lot of theory was developed with the Riemann-Liouville formulation. So it's nice when you have a relationship, clear relationship between these various derivatives and the Riemann-Liouville, because then you can borrow that theory. Okay, so the next derivative is the Grunwald-Letnikov derivative. This is a derivative that was introduced based on the limit definition of the nth order or integer order derivative. So Grunwald-Letnikov derivative is a limit, defined as limit, useful in application because of the the meaningful initial conditions, and it has other properties, which I'll mention also later. Other derivatives that we've come across that we're interested in are the Hadamard derivative, Caputo-Fabrizio, and the Caputo-Catto-Campola that Dr. Devi is going to talk about. Here are some references: Kilbas and his co-authors, and Miller and Ross, again, very good references, and more definitions will be also presented by Dr. Devi. So here's the basic idea. This is the basic idea in the development of the Riemann-Liouville and therefore Caputo derivatives. The idea is the fundamental theorem of calculus, basically, which says that under the proper conditions, the two operators, the derivative operators and the integral operator, are inverse of each other. So when you compose them, you get the identity operator. So this idea then suggests that in an attempt to define fractional derivative, perhaps defining the fractional derivative first is the way to go. And indeed, that's what was done. And to that end, use was made of the Cauchy formula of repeated integration. And you have here at the bottom of the slide the Cauchy formula, which basically states that a multiple integral can be expressed in terms of a single integral, right? So you see the difference now. You have the kernel here, x minus s to the n minus 1 power, and you have here in the denominator the factorial function. So I repeat the Cauchy formula here at the top because that's the formula that was used to define get the generic definition, if you will, of the fractional integral. So you see the factorial function is replaced by the gamma function, and then the integer order n is replaced with alpha. And you have two such formulations, the left-handed case, right-handed case. The left refers to left of x, so the integral here is from a to x, and the right is from x to b. I say generic because these basic forms were used by both Liouville and Riemann to define their respective derivatives. So Riemann uses for a and b 0. So from the Riemann left-handed, you'd have integral from 0 to x, and the right-handed would be from x to 0, whereas Liouville uses positive infinity, negative infinity, respectively, and that's what you see here. And then combining the two, you get, right? And so the integral is from x naught to x, and x is now arbitrary. Part of the definition is that the zeroth order Riemann-Liouville integral is the identity operator. So this is just to show you, to illustrate how different definitions give you different answers for the derivative. So I took the exponential e to the kx, and you see that with the Riemann, you have additional terms here. And the reason these terms appear is because, or I should say, the reason they don't appear in the Liouville integrals is because you have the exponential that's evaluated, the negative exponent. So as the exponent is allowed to go to infinity, the exponential goes to 0. So terms drop out under Liouville, but they don't drop out under Riemann. And this is representative of what happens with all these derivatives. You get different functional forms and different properties. So now that we have the fractional integral, we can define the fractional derivative. And the trick here is to decompose that fractional operator. So the alpha order derivative, fractional derivative, is decomposed into two operators, and m is an integer. So now you have if you decompose it in this order, you have the mth order classical derivative of the m-1 alpha fractional integral. Okay, so, but if you do it in the other order, then you have the m-alpha fractional integral of the mth order classical order derivative. And that's at the heart of both the Riemann-Liouville derivative and the Caputo derivative, as you will see. So here is applying that to the Liouville, the Riemann, and then combining the two, you get the Riemann-Liouville derivatives. Well, an important thing to keep in mind is the fact that you have the ordinary derivative outside the integral, right? So here is when alpha is between 0 and 1, this is alpha in R. So if alpha is arbitrary, then you decompose it and you have this m, whereas here m would be, when alpha is between 0 and 1, m is equal to 1, and you see that you have the regular derivative here outside. This is going to make a big difference, okay? So an example of calculating the Riemann-Liouville derivative, here is x of t is a power of x of t, and you can actually get a closed, this answer for the derivative. Important to note that the derivative then of constant is not 0. So here I have 1, but if you have c, some constant, you would get c times this. So clearly the derivative of constant is not 0. But this result is important because for analytic function that can be expressed as sums of powers of t in this case, you could differentiate term by term. So another important fact and I'm keeping an eye on the clock to make sure I stay within my time limit. Another important fact to note is that here with alpha between 0 and 1, the alpha order integral of the alpha order derivative is not the identity operator. So you get this extra term here. And this is important in initial value problem because oftentimes what you do is transform the differential equation into an integral equation, as you see here. So the left-hand side then, if you're going to integrate this, would bring this additional term here. And notice that x to the super 0 is, as you see here, that creates some issue in terms of singularity at the initial point, right? And so I won't go into this because Dr. McRae is going to talk about this. The Caputo derivative, this is when the order is interchange of the operators. So you see here, because the classical derivative is inside the integral, so you see that if the function is a constant, the derivative of a constant in classical calculus, that's a 0, and that makes a Caputo derivative equal to 0. Right, so interchanging the order of the operator is going to give us takes care of some of the challenges I mentioned, right? And then the advantages are, as I said, initial conditions expressed have the same form as those of ordinary differential equation with integer derivatives. The derivative of a constant is 0, and then you have this nice simple relationship between Riemann-Liouville and Caputo derivatives. And if the initial value is 0, then they coincide. The Gromov-Letnikov derivative, as I told you before, is defined, it's the analog of the limit definition of the classical nth order derivative, right? All I want to mention here is that this, even though you see a summation from k equals 0 to n, this is in fact an infinite series because as h approaches 0, n goes to infinity. So that's a difference between the classical definition, limit definition, and the fractional definition. You do have an infinite series there. Useful properties, well, there is a relationship between Riemann-Liouville and Gromov-Letnikov. Same thing, meaningful initial conditions, And if the derivative exists at some order, then you can show that all derivatives at lower order also exist. So this nice development here from Dr. Lakshmikantam text or monograph on theory of fractional dynamic systems. The other derivative, I'm just right on time, so I'm going to stop here, but this is another interesting way of defining fractional derivative. It's defining higher order fractional derivative directly without paying attention to lower order, right? So it's an interesting way of defining. Again, you find application of these derivatives in physics. As I was telling you, these derivatives are oftentimes defined for specific application, and this is an example. The Riesz derivative has some invariance property, the invariance of the scalar product, for example, right? And you have the generalization of it by Ferrer. So I'm going to stop here, but I do want to mention this text by Herman, Fractional Calculus, an Introduction for Physicists. It's for those of you who have not worked with fractional derivatives, it's easy to read, a lot of applications and so on. So I'm going to stop here. Thank you for your attention. And Dr. McRae is going to talk to you about initial value problems of fractional differential equations. So I'm going to stop my presentation.
Thank you, Zahir.
Yes.
Okay, good morning all. And thank you for inviting us to speak. And I'm going to give some existence results of initial value problems of fractional differential equations. And as Dr. Dreese has already mentioned, why is this not sudden, but why is this interest in fractional differential equations just exploded? Everybody's writing papers on it. It's because, as she said, that in many applications, a fractional differential equation gives a better model for some process rather than the ordinary differential equation. And she mentioned a whole bunch of different fractional derivatives. Most of the results I present would be on Riemann-Liouville, and I think I have one at the end using Caputo. So this is the basic problem that we're going to look at, that the Riemann-Liouville derivative of x is equal to ftx, and the initial condition is given this way. This is, again, as she said, as Dr. Dreese said, since there's a singularity, the initial condition has to be adjusted to look like this. And its corresponding Walter fractional equation is this, so any solution of the differential equation is also a solution of the integral equation. Okay, moving on. And so here's my plan. First, I'll give a couple of existence results, and it results that I'm sure all of you are familiar with in ordinary differential equations. That's Peano's and Picard's theorem, but I will give the fractional analog of it. These results are from the monograph Lakshmikantam et al. Theory of Fractional Dynamic Systems, published in 2009. As a matter of fact, I think most of the results in my presentation will come from this book. Okay. So remember Peano's theorem, that gives you existence, but not uniqueness. And so we have f is bounded on this closed set. And just boundedness gives you the existence of a solution on the interval from t0 to t0 plus alpha, where alpha is given as the minimum of a or b over m times this factor. If you remember in ODEs, what we have is minimum of a and b over m. Here, because of the fractional derivative, you get this additional factor. But other than that, it's completely similar to the ordinary differential equation case. Okay. And then here's Picard's. If you remember, Picard's is the successive approximations, and Picard's gives you not just existence, but also uniqueness. And it gives you uniqueness because in Picard's theorem, in addition to the requirements in the previous theorem, we also ask that the f function satisfy a Lipschitz condition. And because of that, you get a unique solution. And so the successive approximations are defined this way. Typo, this should be a lowercase f. And again, the interval of existence, T0 and T0 plus alpha, where alpha is the minimum of A, B over M. Again, that same factor that comes from the fact that we are dealing with fractional derivatives. Okay, and next I'm going to give some definitions that we use heavily in our work. So one definition is what is a CP continuous function. And a CP continuous function it's continuous on T0T with open at T0, and then T minus T0 raised to the PM of T must be continuous on the closed interval T0 to T. This is where that, this is how it related to how we take the initial condition. And we will define, we had the problem and we have the, what are called lower and upper solutions of the differential equation system. And a function is said to be a lower solution if it satisfies this inequality, that is, the derivative of v is less than or equal to f tv of t, and the initial at the initial condition, v at initial condition is less than or equal to x0. And if the inequalities are reversed, we get the upper solutions. Okay, now we already looked at a couple of existence results, and existence results can be obtained using various approaches. The results that we present here are based on using differential inequalities and comparison theorems. And this was an approach developed by Professor Lakshmikantam and his research group. And the idea is to modify suitably the given problem into a simpler problem and use the known existence results for the simpler problem to establish existence result of the original problem. And this is where we use the comparison theorem and differential inequalities. Also, if you combine the method of upper and lower solutions with this differential inequality approach, that gives us a mechanism to establish theoretical as well as constructive existence results. And the lower and upper solutions that generate the closed set serve as upper and lower bounds for the solutions, or solution as the case might be. So we are going to look at an existence result in the closed set. Okay, so we have, if the upper and lower solutions satisfy this condition and are Holder continuous with exponent lambda bigger than q, such that the lower solution is less than or equal to the upper solution on the interval from T0 to T, and f belongs to that closed sector, then there exists a solution of the initial value problem such that it is sandwiched between the lower solution and the upper solution. So the solution exists and it was bounded above by the upper solution, below by the lower solution. Now, observe that in this result, again taken from Professor Lakshmikantam's book, we require Holder continuity, but Holder continuity can be a bit more than a bit difficult to verify. So subsequently, in 2012, Devi et al. Published a paper, Variational Lyapunov Method for Fractional Differential Equations, and this was published in Computers and Mathematics with Applications, as I said, in 2012. And in that, it was shown that the requirement for Holder continuity can be weaken to CP continuity. And so then this did us to do that. And the lemma says if you have a CP continuous function and on the interval from T0 to T, and for any T1 in here, if M of T1 is 0 and M of T is less than 0 before T1, between T0 and T1, then the derivative at T1 is going to be positive. And this is the basis for proving the following comparison theorem. And the comparison theorem says, okay, so we have V and W that satisfy these two inequalities. Now, with one of these inequalities being strict. So it can either be, this could be less than, strictly less than, and this could stay as it is, or the other way around. So with one of the inequalities being strict, then if we have the initial conditions of V0 and W0 related this way, then we have that V of T is less than equal to W of T on the entire interval. Now, this comparison theorem is a fundamental tool in analyzing FDEs using the approach of differential inequalities and comparison theorems. All right, Dr. Drisi has already talked about this, so I'll just zip through this. Just that there's a relation, we can establish a relation between a Riemann and a Caputo differential equation, and we can show that any Caputo FDE can be transformed into a Riemann-Liouville FDE, and hence the, let's see. So using this particular relation, that the Caputo derivative of X is equal to the Riemann-Liouville derivative of X of T minus X of T0. Using this relation, we can transform any given Caputo into a Riemann-Liouville FDE. And so whatever the solutions of the Caputo FDE will have properties similar to the properties of the Riemann-Liouville FDEs. And therefore, any results that were established using for the Riemann-Liouville FDE will also hold for Caputo FDEs, which is kind of convenient because in applications, this is the Caputo FDEs is used much more than Riemann-Liouville. And my next two results, almost at the end here, we give two constructive methods. Remember, I said if you combine the method of upper and lower solutions and differential inequalities and comparison theorem, you can have theoretical, which we had in the previous theorem, and we can get constructive methods that will yield monotone sequences that converge to the solution of the initial value problem at hand. And each member of these sequences are solutions of some related linear FDEs. And so they can be computed explicitly. And so the importance of these techniques should be apparent. Okay, so for the monotone iterative technique, we require that V and W be upper and lower solutions of the initial value problem, with V of T being less than equal to W of T. And we require this one-sided Lipschitz condition that ftx minus fty must be bigger than or equal to minus m times x minus y, where the lower solution is less than y is less than x, y is less than or equal to x, and both are bounded by the upper and lower solutions. And in the under these conditions, there exist monotone sequences, Vn of t and Wn of t, such that as n goes to infinity, Vn converges to rho of t, Wn converges to r of t uniformly and monotonically. And what are rho and r? Those are the minimal and maximal solutions of the initial value problem. So here we don't necessarily have a unique solution. So we could have maximal and minimal solutions. And so what maximal and minimal solutions are, that they satisfy these equations. They're solutions of these two equations, basically the equation at hand. And so the big thing in this technique is to figure out what linear problems you will use as iterates. And so for the MIT, the VNs are solutions of this. So it's the derivative of the n+1 iterate is equal to f evaluated at t and the previous iterate minus m times Vn+1 minus Vn. So this is then a linear equation, and the initial condition is taken as the same initial condition as our problem at hand. So this gives you the Vn's, and the Wn similarly satisfies this equation. And then once you have the solutions of these equations, you can show that these solutions of linear equations will satisfy using upper and lower solutions and the comparison principle. You can show that the V's are an increasing sequence, the W's are a decreasing sequence. Did I say that right? Yes. And the V's converge to rho and the W's converge to R, the maximal and minimal solutions of the problem, respectively. Okay. And next I will give another result which deals with a constructive technique to obtain the monotone sequences that converge to the solution that we are looking for. The good characteristic of generalized quasi-linearization is that it gives rapid convergence, that in generalized quasi-linearization, the convergence is quadratic, whereas using the MIT, convergence is linear. And as we know, in numerical studies, convergence is always of interest. And so when Bellman came up with his quasi-linearization method in the early part of the last century, he required that the f in the problem should be convex. That is, not only should we have the second derivative with respect to x exist, but that it should also be positive. And here we've weakened the condition. We don't require fxx. So we start the same way. We have, oh, and incidentally, this one I'm setting it up as a Caputo differential equation. So here you can see that we don't have that x of t minus t0, because with Caputo you would have initial conditions which are similar to the types that we have in ordinary differential equations. So we have these two hold, and so upper and lower solutions such that alpha 0 of t is less than beta 0 of t, and initial conditions this way. So instead of asking for convexity, this is the condition that we require, which, as you can see, is weaker than requiring the second derivative. And what we require is, for this technique to work, is that f sub x must exist and be increasing in x for each t, such that f of tx is bigger than or equal to f of ty plus f sub x dy, x minus y, whenever x is bigger than or equal to y. And we require that f sub x be Lipschitz continuous. Given that there exist monotone sequences, alpha n and beta n, such that alpha n converges to rho, beta n converges to R uniformly and monotonically. But here we have a unique solution, right? And so this was instead of looking at 1.1 and 1.2, we were looking at this Caputo FDE. So CDQ is FDX. And as I said before, the initial condition looks like what we are used to in ordinary differential equations. And can get those sequences, and the sequences converge quadratically. So the sequences, building the sequence is the big get of this method. And so for this, generalized quasi-linearization, we take these linear equations so that the derivative of n plus 1 is f of alpha of n, and f sub x evaluated at alpha n, then alpha n plus 1 minus alpha n. The initial condition is the same as the initial condition for the problem that we are trying to solve. And the betas are similarly defined this way. And then we can show that the sequences generated by these FDEs, the alphas are increasing, the betas are decreasing, and they converge uniformly to the unique solution of the problem that we had on the previous page. And quadratic convergence, which was the big cell for this one, is obtained by setting P sub n plus 1 as the difference between the solution and the alpha n plus 1, similarly for R. And with this and a couple of pages of calculations, we would arrive at this, that the Pn plus 1 is less than or equal to n times the norm of max norm of x being squared, right? And with R, you would do a similar process and get the same, a similar relation. And that is all I have to say. And now Dr. Devi will take over and talk about some recent advances in this field. And let me stop sharing. And it's all yours, Vasu.
Thank you, Farzana, and thank you, Zahia, for the nice presentation you have given. Now let me share my screen before we start the talk. So, Dr. Dreesy and Dr. McRae have given the basic fundamentals, the intuitive, mostly the intuitive way to the approach of fractional calculus and fractional differential equations. Because we have not given you the basic theory, we are just giving you a brief survey so that if anyone is interested, they can look into it and learn more. Especially Dr. Dreesy has gone from the fundamentals so that you can follow and develop the subject. And Dr. McRae has given you the approach given by Professor V. Lakshmikantam, where we start working with from the basic lemmas and develop the comparison theorems. Now, in my section, what I'm planning to do is combine both of them and try to give you the latest developments. But first, I would like to give some of the latest work, latest definitions that deal with our relationship between ordinary and fractional derivatives. So if you have seen some definitions of fractional derivatives, the main being Riemann-Liouville, Caputo, Grunwald, Letnikov, and there are many other definitions, and all of them have some drawbacks, which are that except Caputo and Caputo-like, the derivative of a constant is different from 0. And all these fractional derivatives do not satisfy the product rule and quotient rule of differentiation, and they do not have a chain rule, and mean value theorems are not known as in ODEs. Actually, Professor Lakshmikantam's book has a mean value theorem, but it is very, very different, and it needs a definition of a ultra Mittag-Leffler function, if I remember correct. So the search for finding a fractional derivative that would satisfy all these properties that the ordinary derivative satisfies has been going on. And Dr. Khalil et al. Came up with this equation 1, if you can see here, which shows that, which uses in place of f of t plus h, f of t plus ht to the 1 minus alpha. And with this definition, he could show that all the properties of the product rule, quotient rule, etc. could be satisfied. Now, the quest of mathematics is always the quest of generalization. So this has been taken up and then extended by Dr. Kotagampala. And what he did was, in place of f of t plus h, he put f of t e to the ht minus alpha. And you can see that with this, if you linearize e to the ht minus alpha, you will get the term in the Khalil definition. And so this definition of Kotagampala is a generalization of Khalil definition. And this also satisfies all the properties of ordinary derivatives, like product rule, quotient rule, etc. Now, what happened was we were working on a computational project of fractional differential equations. And Dr. Sen came up with another new idea of fractional derivative using these two, Kotagampala's and Khalil's definition. So we name FD Ka as Khalil's definition and FD Kat as Kotagampala's definition. So you take the derivatives from the left-hand side and right-hand side and form a linear system, as you can see, Ax equals to B. The FD on the right-hand side of the equation is, if you can see, FD on the right-hand side of the equation is ordinary derivative. Then you find the values of K1 and K2 use solving this linear system. And then the FD nu was defined as a linear combination of this K1 and K2. And it was observed numerically that this is a better derivative than those of this gives you a better result than those of both Caputo and Kotagampala numerically. Now these results, all the definition and these results have been published in the following research paper, which I quote. Then the question came up, but most of the research did not go in this direction, because the question is not about whether it's a limit concept or whether the fractional derivative follows the ordinary derivative. The importance was of following the applications. The applications, people needed many types of fractional derivatives, and they were concentrating on those derivatives that would give them a better modeling tools. So in that case, Kotagampala again defined a generalized fractional integral. I mean, he left that limit definition, he started this. So with this again, I want you all to recognize one pattern that is coming up. You remember Dr. Drisey's talk, you see the iterated integral over there, you see the Dirichlet technique where the double integral becomes a single integral, and that extends to the nth integral, int. So this is same approach. I mean, if anyone of you want to develop a new theory for fractional differential equations or fractional derivatives or integrals, the idea is simple. You start with some integral, find the nth iterated integral of it, and that will be your kernel. And now what to do is you replace the n with an alpha, which is a real number or a function of t, and then, I'm sorry, I hope I'm audible. And then replace the n-1 factorial function as a generalization function, which is gamma n. See, gamma function is the generalization of factorial function. So you replace it with gamma function, and up you're there with a new integral. But you need to, but the one thing that one needs to remember is, when Riemann-Liouville integral was chosen to be the integral for most of the applications, the reason they chose it was it satisfies most of the properties of integrals of the ordinary integrals. That is, it satisfies the linearity concept and some other properties. So with some things in mind, we can also start defining a fractional derivative. The reason why I'm saying this is because though this area is 300 years old, it is ever new, and every day new definitions are being coming up. I'll show you a couple of them and you can see what I mean. Now this is a Riemann-Liouville Kotagampala fractional derivative. So again, you see, hey, Kotagampala is defining something new, but he is using what all is there. So he has defined an integral, and then similar operator as that Dr. Drisey has shown you, the dt to the n. And then if you put rho equals to 1 in that equation or in the definition, you end up with the Riemann-Liouville ordinary derivative. Now, using the relation between the Caputo derivative and the Riemann-Liouville derivative that both Dr. Drisey and Dr. McRae have shown, he defines the Caputo Kotagampala definition as follows. Now again, as Dr. Tracy has told you all, if the function is analytic and you have a power series, then you can find the derivative of the power series if you can actually calculate the power function next to the nu. And this was done by Kottakampala. So you can find put a Kottakampala derivatives of most of the analytic functions using this formula. Now next, I'll just to show the work that goes parallel with the Dr. McRae's what Dr. McRae has shown. I would try to put a couple of results that are latest that have been taken from fuzzy fractional differential equations under Kaputa-Kottakampala fractional derivative. Okay. Now you can see the initial value problem over there. Now you see the lemma, and the lemma is exactly what Dr. McRae had shown, and actually that lemma has been done by all three of us. So she just said Devi et al. It is all three of us that have solved this wrote this lemma, and this actually gave much leverage because we could leave Holder continuity and start work with continuous functions. So this lemma, you can see if you put m of t equals to u of t minus v of t, then it is exactly what Dr. McRae has shown. And if you take rho equals to 1, it is the Caputo derivative over there. Now this comparison theorem is a little different from what Dr. McRae has shown, but I'll give you the concept behind it. So you have one system that's on the top having the Caputo-Riemann-Liouville derivative of x of t equals to f of t x of t with it's an initial value problem. Now you want to study that equation, suppose, but it's a very complicated equation. Then what you try to do is you try to find a simpler system given by the C d alpha u equals to g of t u of t with u at a equals to u naught, and then try to find a relation between the solution of the considered problem, which is very difficult for us, complicated, and the solution for this. So what you try to do is you try to find a relation between both of them by using the function g of t x of t. See, this we have written c d alpha rho x of t because that was there in the paper, but actually you can write f of t x of t is less than or equal to g of t x of t. That means you are relating the function f and g. If there is a relation between both of them, then you can say that the maximal solution of the simpler system dominates the unknown solution of the complicated system, provided at the initial value, the simpler system initial value dominates that of the complicated system. Now, look at this results have been done in the paper fuzzy fractional differential equations. I would like all of you to notice that this is another new area, fuzzy. Now, with a simple example for those who are new, fuzzy means that you really cannot clearly say what it means. For example, if I take a class of students, I can say by using the numbers or real number scalars, the heights of the people, the marks of the people, but I cannot tell them how good they are in terms of subject or in terms of their behavior without some relativity with some grading. Like I cannot give a number. It's actually a region. So that fuzziness is characterized and became a very big area. Fuzzy arithmetic was defined, then fuzzy algebra was done, and then there is a book on fuzzy differential equations written by Professor Lakshmikantam and his group. So you can see how the research area goes up. Now I'm going to leave this Kottakampala derivative and go to another derivative which is called as Caputo-Fabrizio fractional differential operator or the derivative. Here what they do is you take the Caputo derivative, you had in the kernel, I mean inside the integral, 1 by t minus s to the power of alpha. Now that when you put t equals to s, the integral will blow up. So to take care of that situation, they have used the exponential function over there. Now exponential function is an excellent function. It's a very nice function, has all the most beautiful properties. So it's always a good choice. And then they used a normalizing function to take care of the alpha. So with this, the most important part of this is non-singularity of the kernel. And the authors themselves have said that this model is useful for dealing with a class of real world problems that satisfy the exponential decay law. So here again, I point out that the number of different various fractional derivatives is because of the variety of problems that exists in the world. and all of them cannot be put into one framework, and this is being used as a tool for each type of problems to use a different fractional derivative. So that is the reason why, again, as I said earlier, any one of us who are interested can actually start with a new fractional derivative and work through. Now there is another new definition that was recently given by Atanganu, Bellino, Caputo. Atanganu, I guess. Atanganu and Bellino. So they named it as Atanganu, Bellino, Caputo derivative and called it as ABC x to the alpha t. The alpha is the order of the derivative. And in place of exponential function, they replaced it with the Mittag-Leffler function. Now, Mittag-Leffler function is the corresponding corresponds to the exponential function in fractional setup. So using this, what they did was they said that you can actually approximate the Mittag-Leffler function, and then once you do that, you can actually take the Laplace transforms and work with this. Now here what they studied was they studied the asymptotic solutions of fractional interval differential equations with non-singular kernel derivative. And this is published in Chaos. Now you observe there's something more I want you to look here. They said fractional interval differential equations. Now what does this mean? This means that you take the set of, you take the real line, construct all possible intervals, closed and bounded intervals, and put them in one set. Now you define an addition operator and addition between these two, between two intervals, and define scalar multiplication. Then you end up with a linear space. You define a norm on it. Then you get a norm-linear space. Then you talk about the convergence so that it becomes a complete space or a Banach space. And then you're set to work with differential equations. So this is how the areas develop. And the last thing that I wanted to show you all is we have said that the Caputo fraction, the fractional derivatives are not fractions. They can be real numbers or complex numbers, but also they can be functions of t. So this was defined where this function of t lies between n-1 and n, and this is how it is defined. All you can easily observe that the alpha was replaced by alpha of t. Now what happens is you cannot, most of the theoretical version is not there. Most of his work is done using numerical analysis over here. And that's about it. What we try to do over here is to give you a brief review of what is going on with respect to the field we are working in and with respect to the approach we are working in. There is a lot of approach that is very different. The people have done lots of work in numerical analysis. People have done work using fixed point theorems and so on. And one thing that I would like to say before ending is concluding with Professor Avadani's talk yesterday, that mathematics gives only, that says that the solution exists and it is for others to check. See, it's like this. Mathematics job is to do that there exists a solution and give criteria when a solution exists, give criteria when the solution exists and is unique, give criteria when you can find monotone iterative techniques. That's their job. After that, each individual applied person can work in their own area, see this, check this criteria and know that their modeling is correct and then follow the approach that they need to. Well, with this, I thank the organizers for giving us this chance to present our work. I thank specifically Dr. Captain Sujata, the principal ma'am of St. Joseph's College, Dr. Aruna ma'am, and Dr. KPR Sastri of Uttarandhra Mathematical Society and the Society for in memory of Dr. Meenakshi Sundaram, and Dr. K.N. Murthy garu and Dr. Avadani garu for their support. Thank you so much. Over to you, Madam Dr. Sujata. Over to you, Madam.
Okay, Madam. Thank you. Thank you, Madam. Thank you so much. Thank you for taking your time to prepare for us such an extraordinarily wonderful presentation. That was flawless, Madam. I want to use this note to thank you, madams, for that extraordinarily presentation that you gave, and it was simple yet extraordinarily profound and effective, Madam. There are some questions from participants. Can I read, Madam?
Please.
Hello, there are some questions from participants.
Yes, madam, please, you can read. Yes,
First one, madam, let me know the physical significance and geometrical interpretation of the eigenvalue. Let me know the physical significance and geometrical interpretation of the eigenvalue.
if it is, you're asking for an eigenvalue of the fractional derivative, I hope. Eigenvalue problems of the fractional derivatives that deals with the,
This is
I
from,
think so, because if it is ordinary, I'm sure all of them know.
MBGR Engineering College is asking.
Let us answer the first more simpler question about the derivative of eigenvalue. What do you mean by the physical representation of the fractional derivative itself? I think the eigenvalue comes later, but let's go first to the fractional interpretation, physical and geometrical interpretation of the fractional derivative. So there are two things. We have one paper done with our group dealing with this topic, and what we say is that the alpha in the fractional derivative represents the frictional forces, and therefore the correct choice of alpha will help you to model your physical problem properly. You need not need the you need not use the first derivative, second derivative, so on, as in the ordinary differential equations. If you can choose your correct alpha, then that represents the frictional force and your problem would be simpler. If for the interested participant, I'm going to share the papers that we have done. Similarly, the geometrical significance, again, you can you can take a function, and with various values of changing the alpha, you get a behavior that shows that the change of alpha gives you a different representation of the function, derivative of the function. So the geometrically also, again, I would like to share the paper which we have worked with. But one thing is for sure, different fractional derivatives gives you different representation. They mean different things. So there is no way of giving a unique physical representation or a unique geometrical interpretation for fractional derivatives. It goes, for each thing, it comes differently. Okay, and regarding the eigenvalues, I have not worked in that area, so I cannot answer you that question directly. But again, looking at from what we have done, I can actually say that, again, the interpretation will depend on the specific problem, and we cannot give a unique interpretation or a representation. Thank you.
So one more participant is Mr. Ramasubbarao. He wants to talk regarding question only. Can I allow him, madam?
Please, sir, I think I saw that question. He has a big question, right?
And that is the next one. Is actually he didn't ask, but he wants to raise. He raised a hand, madam.
Yeah, please. Please allow him, madam.
Yes, ma'am. Meanwhile, I will read one more. Actually, I allowed, but it's not coming, I think. Meanwhile, I'll read one more question, madam. Let me know the physical significance and geometrical interpretation of the fractional order derivative.
That's what I have already said. I took the question first.
Okay, it's okay. Yes, ma'am.
Yeah, actually, I saw all the questions, madam. That is
Yes,
the reason
ma'am.
why I took that question first.
What is the best big one? What is the best way to discretize partial derivatives according to the Capito definition? There are many different approaches to the discriminant of partial derivatives, but most of them do not preserve the fundamental properties of the systems described by the continuous time equation, such as system stability. For example, a discontinuous continuous fractional system becomes asymptotically stable after discretization using the modified Grunwald and formula. Is there any known method of discretization knowledge that preserves the properties of the original system?
Madam, the one before the last slide, I guess, I have talked about that ABC derivative. That is the latest one that has come up, and the authors claim that they can it caters to many types of problems, and especially this asymptotic behavior. So maybe the person who asked this question can look into that paper and see if it helps him.
Okay, ma'am. Madam, one more, how this topic is related to COVID-19, please explain. Any
Okay.
relation is there?
Okay, I was looking at it directly, not this problem. You can model, because see, all that you do is you have the data, and I'm sorry, I did not prepare that slide, but what you let's look at a simple problem where suppose X is the number of people infected and Y is the number of people susceptible. Then in ordinary differential equation, you would write dx by dt is equal to the infected people minus the susceptible people. So minus alpha x plus beta y or something like that. And dy by dt is equal to minus plus alpha x and plus beta y. So sorry, plus gamma x and plus delta y or something. So you get a system where you okay, no, I'll put it in a still simpler way. Suppose the rate of change of infected people is rate of the rate of change of infected people will give you the more what should I say, the more serious that they will the infected people will actually infect the susceptible people more. So you can say that the rate of change of susceptible people to infected people is dependent on the infected people. I guess saying this online is very difficult. But if you look at any prey-predator model, that's the simplest way to put it. You can look at any prey-predator model, and suppose the prey is the susceptible people and the predator is the infected people, and you can write down the mathematical model. Now you can actually construct the, excuse me, is there anyone saying something that can help me out?
No.
And then instead of the ordinary derivative, you can construct the fractional derivative and try the mathematical modeling. There is one paper by Dr. Nito and his group on COVID-19. Maybe Dr. Drisi, can you please type that paper reference? That they have actually worked on the Wuhan population, and they came up with a mathematical model that has about 10 equations. So there is a mathematical model, and that has been worked on it. And actually it's an ordinary differential, it to fractional differential equations and work with the COVID-19. And there is another area which I have said, as I talked about this fuzzy and interval differential equations. These two fuzzy differential equations and interval differential equations are subset of what are called as set differential equations. And where the elements in there are sets, compact convex sets. Now, if you can take any compact convex set, you can take a disk, a closed disk as a compact convex set. So right now, this 200 meters radius containment zone, you can consider it as a compact convex set, and then you can try to mathematically model it using set differential equations. But these require a lot of data to validify your work, and that's the most difficult part. So I'm sorry for a few minutes where I could not properly present what I meant to say, but you can actually look at the prey-predator model and develop the COVID model also. If you have two variables, one is the infected people and one is the susceptible people. Thank you.
Now, madam, one more is there. Is it useful for solving problems related to fluid dynamics?
Yes, sir. Everyone is using everywhere, and they say that the results are very wonderful. If you talk to engineers, they're much more happier than the mathematicians because they do not need whether the math is correctly satisfied or not. If it works for them, they're happy. And they say that, in fact, there are lots of workshops going on fractional differential equations where they're only concentrating on the applied areas, where they're teaching you how to use them and apply them to their own area. You have, I'm sure there are papers in fluid dynamics also, though I have not worked with them or have not studied them. In fact, I've seen papers more in mechanical engineering rather than fluid dynamics, but I'm sure it will work out.
One
See,
more
all
is
you need to do is, one second, all you need to do is try to put in fractional derivative of your choice, which you think is useful in your area, into the ordinary differential equation you have and try to work it out. Try do some numerical simulation and see what's going on.
Okay, ma'am. One more is there, madam. Requesting you to address Hadamard fractional and order fractional differential equations.
Excuse me, madam.
Hadamard fractional and order fractional differential equations.
Well, Hadamard fractional derivative has been generalized to Kaputa-Kartagampala. Because of lack of time, we have not gone through it. But the idea behind Kaputa-Kartagampala derivative is that it is a generalization of Riemann-Liouville and Hadamard fractional derivatives.
Madam, so many participants are asking, please, can you share your PPTs? Please share PPTs like that. Can we share?
Well, Dr. Drisi, what would you say, Dr. McRae?
Dr.
They want
Drisi,
us to share
madam,
the PPT?
they're asking your PPTs, man. They are
I suppose we could send them.
Yeah, okay. Fazan, Zahia?
She has to unmute. I think.
You have to unmute. You have to unmute.
Sorry. Sorry. Yeah, it's okay. We could send them with the references as well.
Okay,
Yeah.
we will update it and send it to you all.
So
They
they may,
will send it to you.
yes, ma'am. I can forward it to their mail IDs.
Okay.
Yes, ma'am.
Well, I guess we are already very late, madam.
It's okay, madam. Then, so we are going to close now. No more questions, I think so, from the participants. I'll wholeheartedly thank you, resource persons, Professor J. Vasundhara Devi, madam, and Jahia Drisi and Farzana McRae. Your content today will be echoed in our minds for a long time to come. Thank you, madams. It's late night and sorry I arranged it this time because no other way to conduct. If it is the evening, we will get the early morning. So that's why I've chosen this time, madam. Thank you so much. Thank you very much. And now, can I proceed next session, madam?
Okay, thank you so much. Yeah, thank you very much.
Thank you, madam. Thank you, Drisi, madam, and McRae, madam. Vasundhara, madam, thank you, madam. I'll proceed to the next.
Thank you. Okay.
Thank you.
Yeah, we are stop staring the screen. Okay.
Can you please be there one hour? It will be over, madam. Can you be there?
Yeah, I'll be there. I don't know about them.
What about Drisi, madam, and McRae, madam?
Yeah, we'll be there.
Yes, yes. Thank you so much. Thank you so much, madam. Now I invite Mr. S. Sriram, Assistant Professor, Department of Mathematics, to introduce a resource person, Dr. K.N.V. Varaprasad Garu, who will talk about the existence of fixed point theorems in metric space with weak distance. Over to Mr. Sriram.
Thank you, ma'am. So good morning to one and all. It's my privilege to introduce eminent speaker, Dr. K.N.V. Varaprasad Garu. Sir completed his MS in 1995 from Barkatullah Vishwavidyalaya, Bhopal. Sir completed MPhil in 1998 under the guidance of eminent Professor R. Bhaskaran Garu from University of Madras, Chennai. Sir completed PhD in 2008 under the guidance of eminent Professor GVR Babu Garu from Andhra University, Visakhapatnam. Sir working experience is 21 years. He worked as a lecturer in Dr. L.B. Dr. Langapalli Bullaya College, Visakhapatnam from 1999 to 2012. Now he is working as a assistant professor in Guru Ghasidas Vishwavidyalaya, Central University, Bilaspur. His research area is on fixed point theory and applications. Now, number of papers published were 22. He attended 34 workshops and conferences. He had given 4 paper presentations. Under his guidance, 2 students are doing PhDs. And thank you. Now I request sir should take over the session. Thank you.
Thank you, Sri Ram. Sir, you can take over the session, sir. Sir, are you here?
Thank you very
Sir,
much,
welcome, sir.
Dr. Sridhar sir. My name is Prasad. Already Sridhar sir has introduced me. First of all, before starting off my lecture, I would like to thanks to Dr. Captain Sujata Madam and retired professor, eminent Professor KPR Sastri Garu. Today my lecture is my video? Where is my video? Okay, my screen. Videos. Oh, sure. Okay. Today's my topic is that the existence of fixed point theorems in metric spaces via W distance. This is today's lecture. Big screen over, no? This is one of the important tool is fixed point theory. The theory of a fixed point is one of the most powerful tool of modern mathematical analysis.
Not visible, sir.
Not visible?
You have to screen.
Sir, hello.
Hello.
Sir, please share the screen, sir. So there is a bottom of the screen.
In the down,
There is
Bottom of the screen, there is a screen share option. Share screen.
Share screen.
Share screen, sir. So green color, share screen.
arrow is there, sir. Arrow. Screen, share screen arrow is there. In the down, sir. We will.
Okay.
So click that share screen option, sir.
Oh, share screen.
Yes, yes. Share screen.
The bottom, sir.
There is a
Bottom.
green color, sir. Yes, sir. Now it's yes, sir. Visible, sir. Thank you.
Okay. Video? Now
It's a visible, sir. It's visible and audible also.
Thank you.
It's good, sir. It's good to continue, sir.
May
Thank
I
you.
start now?
Yes,
Okay.
sir. You can start.
Okay. The theory of fixed points is one of the most powerful tool of mathematical analysis. Theorem concerning the existence of properties of fixed points are known as fixed point theorem. Fixed point theory is a beautiful mixture of analysis, topology, geometry, which has many applications in various fields, such as mathematics, engineering, physics, economics, game theory, biology, chemistry, optimization theory, and approximation theory, and extra. Fixed point theory has its own importance and developed tremendously for the past several decades. So the important principle is that the Banach contraction principle is one of the famous tools for the solving in many branches in mathematical analysis. Several mathematicians generalized Banach contraction principle in many ways. So one of the important result is Cannon's proof. In fact, Banach contraction principle is forced to be continuous For discontinuous wave, Kannan proved a fixed point theorem for a map satisfying contractive condition that did not require continuity in each point. So, in the other hand, recently in 2004, the concept of weak contraction presented by Birinde, it was published in a nonlinear forum, approximation fixed point of weak contractions using Picard iteration, and he's developed weak contraction. But in another paper, same other Karpathin, it was published in a journal, Karpathin Journal of Mathematics in 2008. The same author is renames it as an almost contractions. Of course, it is appropriate. In the same paper, Birinde established some fixed point theorems for almost contractions in complete metric spaces. He shown in this paper, any contraction, the Kannan, Zamfirescu mappings, as well as a large class of a quasi contractions are all almost contractions. The almost contraction mapping, the definition is that let XD be a metric space and a T be a self map on X is called a almost contraction if there exists a constant delta lies in open interval 0, 1 and some L greater than or equal to 0 such that d of tx ty less than or equal to d of xy plus L times of d of ytx for all x, y, and x. And recently, Jivar, Babu and all published a research paper. It was published in Karpathy Journal of Mathematics. A note on a fixed point theorem of Birinde and weak contractions. Babu and all considered the class of mappings that satisfy condition B. Let definition of condition B is that let XD be a metric space and a T be a self map on X satisfying the condition B if there exists a constant delta lies in 0, 1 and some L greater than 0 such that d of tx ty less than or equal to delta times d of xy plus L times minimum of d of xtx, d of xty, and d of txy and d of yty. Babu and all proved the existence of fixed point theorem for such mappings on a complete metric spaces. They are also discussed in detail about quasi-contraction, almost contraction, and the class of mappings that satisfying condition B. In that paper, others provided in examples the relations between these mappings. In the same way, in 2012, Sirik and al., it was published in Applied Mathematics Computation. They introduced the concept of almost generalized contractive condition mappings and proved some existence theorems of fixed points for such mappings in ordered complete metric spaces. In fact, in that paper, Sirik is provided the following definition, that is XD be a complete metric space, and T be a self map on X is called almost generalized contractive condition if there is a delta lies between 0 to 1 and L greater than or equal to 0 such that of course in this definition actually Sirik is defined in a D, unfortunately it is typed in P. D of tx ty less than or equal to delta times maximum of P of d of xy, d of xtx, d of yty plus half times d of xty plus d of ytx plus L times minimum of d of xy, d of xty, d of yty, and d of ytx. In the now definition is the W distance definition I am going to begin now. In 1996, Takahashi's team, that is Kada and all, Takahashi's team is published in a mathematical Japanica paper in journal, had introduced the concept of W distances in a metric space and proved some fixed point theorems in complete metric spaces. They give some examples of W distances and improved Characteristic fixed point theorem, Eckland's epsilon variational principle, and the non-convex minimization theorem according to Takahasi results. So the definition of the W distance is that follows as that XD be a metric space endowed with a metric D, a function P from x cross x2 tends to R plus is called a W distance on X if it is satisfying the following conditions. Condition 1 is that P of xz less than or equal to P of xy plus P of yz for any x, y, z in X. Second condition is that P is a lower semi-continuous in its second variable, that is if x in X and y in Y in X, then P of xy less than or equal to limit infimum P of xyn. And the last one is that for each epsilon positive, there is just a delta positive such that P of xz less than or equal to delta and P of zy less than or equal to delta implies that P of xy less than or equal to epsilon. So the counter example I'm going to be give now, if capital X is equal to 1 by n, intersection 0, for any xy in X, d of xy is equal to x plus y, if x not equal to y, and d of xy equal to 0, if x equal to y, is a metric on X, and xd is a complete metric space. Moreover, by defining P of xy is equal to y, P is a W distance on X. In this function, this is the not an intersection, this is the union now. So one of the most important lemmas I'm going to be give, this is also proved by Kada and al. Let xd be a metric spaces and P be a W distance on X. The first point is that if xn is a sequence in X such that limit P of xn in X is equal to limit P of xn y is equal to 0, then X equal to y. Second one is that if P of xn yn less than or equal to alpha n, P of xn y less than or equal to beta n for any n in n, where alpha n and beta n are sequences in the 0 to infinity converging to 0, then yn is converges to y. Let P be a W distance on metric space xd and xn be a sequence in X such that for each epsilon positive, there exists an n epsilon is in capital N such that m greater than n epsilon implies P of xn xm less than or equal to epsilon. The sequence xn is a quotient. Now we are going to be provide now some results which are published with P distance function. In 2009, A. Rajani and al. is published a paper, a fixed point theorem for phi psi P contractive map on a complete metric space via W distance. He published and he proved a theorem following: let P be a W distance on a complete metric space XD and phi in phi and psi in psi. Suppose that T is a phi psi P contractive map on X. That is, condition map is that for each xy in X, phi of P of Tx Ty less than or equal to psi of phi of P of xy, then T has a unique fixed point in X. Moreover, limit T power n X is a fixed point of T in X, and phi and psi is defined later. And weak contractive contractions via W distance. Recently, B. Rhodes and al. published a paper in Applied Mathematics Computation 2013 follows as: let P be a W distance on complete metric space XD. Suppose that T be a self map on X is such that phi of Tx Ty less than or equal to phi of P of xy minus psi of P of xy for each xy in X, then there exists a U in X such that U is equal to Tu. Moreover, if V is equal to TV, then P of VB is equal to 0, where phi in phi and psi in psi. The phi is the defined here. Phi is the set of a class mappings of verifying. that is r plus 2r plus satisfying continuous and then non-decreasing phi of t is equal to 0 if and only if t equal to 0. And capital psi is the family of functions of a psi r plus 2r plus satisfying lower semi-continuous psi of t equal to 0 if and only if t equal to 0. In the same paper, others proved another result which improves above theorem for phi psi p weakly contractive mappings. That result is follows as: let P be a W distance on a complete metric spaces XD. Suppose T be a self map on X is such that phi of T of Tx T square X less than or equal to phi of P of X Tx minus the psi of P of X Tx for each X in X, such that conditions one is that either infimum P of XY plus P of XTX is positive, then there is just a u in X such that u is equal to u. Moreover, if v is equal to tv, then P of v comma v equal to 0. And same others, B. Rhodes and all published another paper recently in 2019. It was published in Applied Mathematics and Computation. Let P be a W distance on a complete metric spaces XD such that P of X is equal to 0 for all X in X. Suppose that T is a self map on X is such that for all X in X, P of XTX and TXTY less than or equal to M of XY minus phi of M of XY, where capital M of XY is equal to maximum of P of XY, P of XTX, P of YTY, half times of P of XTY plus P of TXY, and phi in phi. This phi is defined here. This is the set of a class mappings of continuous functions. Phi is r plus 2r plus with a set of non-decreasing continuous with the following conditions. First condition is phi of t is positive for t positive and phi of 0 equal to 0. And the second is that for each Tn is subset of 0 to infinity, Tn tends to 0 if and only if phi of Tn tends to 0. Suppose that either one infimum P of xw plus P of xtx such that x belongs to x is a positive for every w belongs to x and w not equal to tw, or then t has a unique fixed point. In the same paper, others generalized above theorem with using Meir-Killer function and proved some applications integral type. For this further details, you can see this above reference paper. So my main result is that I would like to presenting my result is that let P be a W distance function and a complete metric space XD such that P of XX is equal to 0 for all X in X. Suppose that T be a self map on X such that satisfying the condition almost generalized contractive condition, and suppose that either infimum P of XW plus P of XTX such that X belongs to X is positive for every W in X and W not equal to TW, or the mapping T is continuous, then T has a unique fixed point in X. So this is a proposed proof. My proof is that in the 4 steps, the proof is that first X naught in X, and I define the sequence xn by xn plus 1 is equal to txn for each n greater than equal to 0. If xn plus 1 is equal to xn for some n, then xn is a fixed point of t. Therefore, we shall assume that xn plus 1 not equal to xn for each n in n. In first steps, step 1 is that first of all, you need to prove that p of xn and xn plus 1 tends to 0. This is p is not satisfying symmetric condition, therefore need to show that p of xn plus 1 xn tends to 0 also need to show. Therefore, first is that p of xn plus 1 tends to 0 by taking x is equal to xn and y equal to xn minus 1 in the above inequality. In routine calculation, for taking a n large n tends to infinity, we are getting a P of xn plus 1 tends to 0. Second step is that we claim that the sequence xn is a quotient. This is also routine part, as well as showing that a P of xn xm tends to 0. The important step is that convergent, if it is a Cauchy sequence and a complete or space X is a complete metric space, sequence xn is a Cauchy, then it is a convergent to point u. If you say that is a point, convergent point is a u, we need to show that u is a fixed point of T. The first step 3 is we are going to be shown that point u is a fixed point of T. By step 1 and step 2, we know that that is a converging point A. So the proof of step 3 is that by Cauchy definition, for any epsilon positive, there is just n epsilon is in n such that n greater than n epsilon implies that P of x n epsilon comma xn less than epsilon. But xn tends to u, it will be get from the previous step 1 and step 2, and P of x comma dot is a lower semi-continuous. It is the property of a P definition. Thus, P of x and epsilon u implies that limit infimum P of x and epsilon xn less than or equal to epsilon. Now consider the set x and epsilon is equal to x and k, and epsilon is equal to 1 by k. Then we obtain that limit n tends to infinity, P of x and k u is equal to 0. So now in the statement from, we are going to be assume that first is the case 1. Suppose that u not equal to tu. Then we have a 0 is a, of course condition is a positive, therefore 0 less than infimum P of xu plus P of x dx, x belongs to capital X, less than or equal to infimum P of xn comma u plus P of xn plus 1 n in n, as n tends to 0, as n tends to infinity. Therefore we are getting a contradiction by applying the step 1 and step 2, therefore u equal to tu. Suppose if the condition is not assumption, in the next we go for the case 2. Suppose that there is just a w in x with w not equal to u, and assume that the infimum part is equal to 0 as n tends to infinity. So therefore in this case, then there is just a sequence according to the second line. According to this line, there is just a sequence xn, P of xn w plus P of xn tends to 0 as n tends to infinity. This leads to, we can say that first convert both the summation is 0. That means of P of this term is also tends to 0, and this is also tends to 0. So Cardan, we are going to be use Takahashi's lemma, that is Txn tends to w as n tends to infinity. Now taking a x is equal to xn and y equal to Txn in our inequality, P of Txn, if you are applying then a P of Txn T square xn less than or equal to m of xn Txn plus n of xn Txn. This m of xn and m of xn Txn, n of xn Txn, both are, this is already defined in the statement inequality. This is the maximum times of a 4 terms, and this is the minimum times of a 4 terms. As n tends to t, we are getting P of Txn T square xn tends to infinity, and P of xn Txn tends to infinity. Then from that lemma, we are getting a T square xn tends to Txn. It is easy to identify that from the continuity of a T. This is the second condition. From continuity of T, we have Ty is equal to Y is the contradiction. If W is different from TW, then P of xn W, P of xn Txn is a positive. Then by case 1, again, if it comes that it is turned to the case 1, then we will get the desired result. So last one is a uniqueness part. by routine process, we obtain the uniqueness by using the above inequality. Of course, this is the using of 2 times. We are going to P of x z is equal to 0 and P of z x is equal to 0 part we are going to be used. And this is the supporting example I'm going to provide. This is important is that the condition of infimum part is also essential. The following example gives the importance about the condition. Let us take x is equal to 0 to 1 and define T be a self map on x by Tx is equal to 1. If x is equal to 0 and Tx is equal to x by 2, if x different from 0, define P of x is equal to x minus Ty. This example holds all the properties of the above theorem except infimum condition. Therefore, T has a no fixed point. That means of infimum condition is essential, and it is now and supporting example is another supporting example I'm going to be give here. Capital X is equal to 0 to 1 and define T be a self map on x by Tx is equal to 1 by 4. If x is equal to 0 and Tx is equal to x by 2, if x is different from 0, define P of xy is equal to modulus of x minus y. This example holds for all the properties of the above theorem. And here we observe that easily 1 by 4 is a fixed point of T. And the one another theorem is that the PV, let P be a W distance on a complete metric space such that P of xx equal to 0 for all x and x. Suppose that the T be a self map on x and satisfying condition B, then T has a unique fixed point. So first, actually, in condition B, Babu and all proved in and it was published in Carpathian Journal. In this theorem, there is no need to infimum and such conditions, not necessary for proving of this theorem with using of the W distance functions. Therefore, it is a simple, there is no that much of easy difficulty part. Therefore, it is easy to prove that this proof is also same as well as same as lines above the above theorem. And it is also these two results also not published anywhere. And also the W distance also extended. W distance also extended in Menger space also, that is also defined in R distance spaces. This is my talk here. Thank you very much for giving this opportunity to our Department of Mathematics at St. Joseph College. Thank you very much, madam.
Thank you, sir. Thank you so much. I greatly appreciate the presentation you gave it, sir. It was a nothing short, incredibly informative and interesting, sir. Sir, some questions I'll check and I'll read it, sir. From chat box.
Okay, madam, please.
All are there. They wrote excellent, well presentation like that. They are given, sir. Wonderful, sir, like that. No questions till now. So nice, sir. It's my subject also. I enjoyed. It's a nice presentation.
Thank you.
Then, so we are grateful and very enlightening speech of Dr. KNV Varaprasad Garu. Once again, thank you so much, sir.
Once again, I thank you very much for giving this opportunity to organizers and St. Joseph College management also. Thank you very much, madam.
Thank you, sir. Thank you. Then I'm going to end with this program with a vote of thanks. Coming to the last vote of thanks, we are going to end with the program. Good morning, everyone. Respected resource persons, Principal Dr. Sister Shaiji, Vice Principal Sister Hema, Secretary Sister Mary, IQAC Coordinator Professor P. Sarada, Executive Members of UASMS and SMSMS, lecturers, colleagues, students, research scholars, and all my dear friends. A very good morning to all of you. As a coordinator of this webinar, it is my pleasure and privilege to propose a formal vote of thanks at the end of this two-day informative and enlightening webinar. Before I propose a formal vote of thanks, I would like to share a few words about the Department of Mathematics, St. Joseph's College for Women Autonomous, with which I have been associated for 2.5 decades. The mathematics department is one of the oldest departments in the college, established in the year 1958. Mathematics was offered in combination with physics and chemistry in 1958 to 59. Later, it was extended along with physics and computer science in 1990 to 91. Economics and computers in 2008 to 9, and latest with statistics and computer science in 2016 to 17. The popularity of the department has led the college to start PG course in mathematics in 2003, which is running successfully. Most of the alumni attribute their success in professional careers to their learning of mathematics in St. Joseph's College for Women Autonomous. Apart from teaching core mathematics to MPC, MP computers, and maths economics computers, maths statistics computer students, the Department of Mathematics is involved in teaching analytical skills to all the UG students of the college. The department plays a pivotal role in training final year UG students for placements by teaching them analytical skills as well as quantitative aptitude. The Department of Mathematics has entered into Memorandum of Understanding with Uttarandhra Society for Mathematical Sciences, that is the UASMS, and Professor S. Meenakshi Sundaram Memorial Society, SMSMS, engaged in skill development programs, education and R&D services. As no program can become successful with a single person, I extend my big thanks to all the people worked for the smooth conduct of this event. I wholeheartedly thank our resource persons for the international webinar, Professor K. N. Murthy Garu, Professor P. S. Avadani Garu, Professor J. Vasundhara Devi Madam, Dr. Jahia Drissi Madam, and Dr. Farzana A. Mekre Madam, and Dr. K. N. V. Prasad Garu, and all the participants. Total 853 registered for their active participation. I am very much thankful to the principal, Dr. Sister Shaiji, management, advisory committee, organizing committee, and IT team who worked really hard in organizing this webinar. I am also indeed very grateful to the department faculty members who have given enormous support to make this program successful. I also extend my thanks to the executive members of UASMS and SMSMS for their huge cooperation in this lucrative webinar. UASMS executive members are Professor KPR Sastriyar is the chairman, and KK Sarmagaru is the president, vice president Dr. CH Srinivasarao, and the secretary myself, Dr. Captain K. Sujata, joint secretary Kameswari Madam, and other members are there, and for their cooperation in this lucrative webinar. I want to express my sincere gratitude Professor KPR Sastry Garu from the beginning to end. She is a retired professor of Department of Mathematics, Andhra University, Visakhapatnam, who is the chairman of UASMS and president of SMSMS, for his constant support. From the beginning to the end, he has given the constant support to me and guidance. My special thanks to former executive members of SMSMS, Professor Arunachalam Garu and Mr. Vani Prasad Garu. My sincere thanks to Mrs. Girija Sharma, who is the daughter of Professor S. Meenakshi Sundaram. And my sincere thanks again to Mrs. P. Krishna Kumari Madam, former head of the Department of Mathematics, St. Joseph's College for Women Autonomous. Last but not the least, I extend my big thanks to all our IT team members worked day in and day out for the effective conduct of this international webinar. Thank you, one and all. for being a part of this event and making it a memorable one. Thank you. Thanks a lot and thank you once again. Dear participants, the feedback form is sent to your respective mail IDs. It opens after the completion of the webinar for 1 hour. Please fill the form to obtain the certificate. Thank you, sir. Thank you, all the resource persons who are here. Thank you so much. Thank you, participants. Thank you, our close department members, our colleagues. And now we are, please raise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, Ash.
Thank you, madam. Thank you, Vasundhara madam. Thank you so much. Disi madam, thank you.
Thank you. Thank you.
Megre madam, thank you so much.
Yes, thank you very much for inviting us.
Bye-bye.
Bye.
Share your PPT, madam. Please share your PPT.
We will. We will do that.
So that we will send to their mail IDs.
Okay.
So many they are asking me.
Okay,
Nice
we will.
meeting you, madam. Nice meeting you.
Bye-bye.
Nice
Bye bye.
meeting you. Bye.
Thank you, Faraprasad sir. Thank you, sir. Bye, madam.
Bye.